Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
To this lecture by Alon Lavie. We're really fortunate that Alon would spend an extra day. Yesterday he gave a different talk at the newly formed Turing Center at UW, and so we're kind of piggybacking on that invitation. Alon's going to give a talk about multi-engine machine translation, but we got to choose from several different presentations, and METEOR is one of them. Alon has done some interesting work on MT evaluation, as well as working on machine translation for language pairs where there's very little data. So if you're interested in that later on, we could also ask him. Thank you for coming.
Thank you very much, Luciana. It's really a pleasure to be here. I've known quite a lot of the people in the audience for quite a while. I've never actually been here during my business, so really happy to be here. So I want to talk today about two things, I guess. The original time was to talk about multi-engine MT, so what we've been doing in the last year and a half, but there was also quite a bit of interest in METEOR, which is automatic metrics for MT evaluation that we've been working on, and we've indicated there's quite a bit of interest in that as well, and some of the evaluation results on multi-engine we've done primarily with METEOR. I thought maybe I'd start and to tell you guys a little bit about METEOR, and postpone maybe some of the details of the concrete evaluations that we've done with METEOR. I'm sorry.
That must be better. Okay, so I'll give you the general sort of set, details about METEOR. I'll skip some of the slides about the detailed evaluations, comparing METEOR with BLUE and kind of evaluations, and then I can come back to that if there's interest to hearing more about that. And then I'll go and tell you about our work on multi-engine MT. I also have, if the internet connection works, I can show a demo for a few minutes about the multi-engine approach, and then I can come back and show some more evaluations on METEOR if that's of interest. So let me start a little bit about METEOR. So METEOR follows basically the motivation for it. It is similar to the motivation that originated when IBM developed the BLUE metric. So it falls into this class of automatic metrics that rely on similarity-based MT evaluation metrics, where we're trying to assess the quality of an MT system by comparing the output with human-produced reference translations. And the premise of that, of course, is that the more similar, understood idea is that the more similar in meaning the translation is to the reference, the better. So the goal is basically to build an algorithm that's capable of accurately approximating that similarity. And there's been a wide range of metrics that came before even BLUE that try and do similar things. So edit distance metrics, n-gram-based metrics are trying to do the same thing. But most of those metrics have basically focused, rather than trying to go deeper into capturing similarity and meaning, they go and basically do matching of identical words between the actual translation and the output. And one of the things I want you to sort of, the ideas that I want you to see coming from METEOR is that if you're relying just on perfect word matching between an MT output and a reference translation to approximate similarity in meaning, that's a very crude measure over which to do that. So in METEOR we're trying to do quite a bit better by incorporating more information than just identical matches of words. So this is what you would presumably want from an automatic metric to have. Sort of the ultimate automatic metric would have very high levels of correlation with quantified notions of human notions of translation quality, would be sensitive to small differences in MT quality between systems and between versions of the same system, would be consistent, reliable, general in the sense it's applicable to a wide range of domains and applications, and would be easy and fast and lightweight to run. So you could run it easily and often. So here's some weaknesses that we had observed in BLUE that sort of motivated this work sort of took us in the direction that we took METEOR. So we didn't like some things that we noticed about BLUE, and we tried to address some of them so far, not all of them. So in particular, BLUE basically depends on matching word n-grams of the MT translation with multiple reference translations simultaneously. And as a result of that, they've gone with a precision-based metric, because the notion of calculating the recall against multiple reference translations simultaneously was unclear what that notion would be. So they basically said, we're just going to look at precision, meaning how many of the words from our actual translation occur in any one of these reference translations, comparing to multiple reference translations simultaneously, presumably to overcome this problem of translation can be expressed in many different ways. So maybe our translation didn't get it exactly the way reference 1 did, but we'll find some matches against reference 2 or reference 3. So, so they build a precision-based metric. And the question really is this better than matching with each reference translation separately and selecting the best match and incorporating, again, some notions of recall in the metric? And so we basically went and did this other choice. We actually compare multiple reference translations. We compare with each one separately, and we pick the best match. Now, because it was a precision-based metric, BLUE basically compensates for the lack of recall in their metric by factoring what they call a brevity penalty. So if you're producing translations that are very short and therefore boosting your precision by getting basically translations that are really short and getting then high precision because the words in those translations are going to be correct, but you don't get everything, then you're going to penalize you with a brevity penalty. But that brevity penalty is basically trained once. They have a function that they've trained. It's not sensitive to any particular scenario. And the question is really, well, is the brevity penalty that they built into BLUE adequate in compensating for the lack of recall in the metric? And so in METEOR, we've actually incorporated recall back significantly, and we show that that actually is extremely important. So the third point is that BLUE's n-gram matching requires only exact word matches, and the question that we try to address is, can stemming and synonyms in the matching between MT output and reference translation improve the actual underlying similarity measure and therefore improve the correlation with human scores on MT quality? And we've done that in METEOR. All words are basically weighed equally in BLUE. So there's a question if you want to basically incorporate a scheme for weighing word contributions based on some measures of importance or other types of things. We haven't actually quite yet done much in this addressing this question in METEOR, although that's one of the things that we're investigating and planning to do. And finally, BLUE tries to account for fluency, or how grammatical the actual MT output is, by looking not just at unigram matches across the reference with the reference translation, but looking at higher order n-grams. So the underlying assumption is that if you're getting higher order n-grams, then you're getting the sentence the MT output is more grammatical, and the words are basically in the places that you would expect them to be compared to the reference. And the n-grams there are geometrically average. And the question we had is basically whether that is the best way to capture the fluency or the grammaticality of the actual MT output. So in particular, because this geometric averaging is extremely volatile to zero scores. So if you don't get higher n-grams with geometric averaging, the BLUE score was going to be just 0 if you're trying to assess it on a sentence-by-sentence level. So they actually didn't design the metric to be able to actually assess quality on a sentence-by-sentence level. They basically accumulate aggregate statistics over an entire test set. And we think it's actually very important to be able to assess the quality of translation on a sentence-by-sentence level. And by doing that, you'll actually get a metric that's extremely more sensitive than BLUE is to small differences. And you'll also be able to look at smaller subsets of sentences on which you're interested to see if there's difference in translation on those. So, so basically, the direction that we went to in METEOR is that we actually went back to unigram metrics in terms of the matching. So we're looking at unigram precision, unigram recall, and other types of statistics that can be calculated from the unigram statistics. But in addition to that, we're also adding an explicit component that assesses how fluent or grammatical the actual MT output is fundamentally how well ordered are the words that we match between the MT output and the reference are with respect to the reference. So if they're, the more well ordered they are compared to the reference, basically we're actually going to add a penalty to the metric that penalizes for the words not creating runs of n-grams that are longer, as you'll see in a few minutes. We also then match with each reference separately and select the best match, as I said, rather than trying to match simultaneously against all of the references. And one of the main important things is that we're actually adding, we're generalizing these unigram matches. So instead of just looking and see what words appear identical between the MT output and the reference, we're actually explicitly matching those words and then generalizing, considering not just exact words, but also words that are identical after stemming, so morphological variants of the same word, and then extending this further to try and capture directly synonyms, so that are just synonymous but don't even share a stem or anything like that. So, so the main ideas in METEOR, again, reintroduce recall and combine it with precision as score components. We only look at unigram precision and recall, but we look at not even just a balanced combination of precision and recall, the standard F1 measure, but we actually did experiments and found that in order to get higher levels of correlation with human judgments, it's actually more important to get recall. The recall count actually is more important for correlation with human judgments than precision is. So on training data, we actually got a balance that is, here on this previous slide, appeared as this F-mean measure, which is in fact something that's like a 90% emphasis on recall and only 10% emphasis on precision.
It says the opposite on the slide.
No, actually, if this is, yeah, if you actually like work it out, this is actually a recall-heavy geometric combination of those. So, so we got that balance between those was done on some training data, and then we're calculating those statistics as well. So then the matching takes into account, as I said, word inflection variations and synonyms. And what we do is before we actually calculate this, we run this match. We have a matcher program that aligns the MT output with each reference individually, and then calculates a score for that match and takes the best one, the best pairing. And then we address the fluency issue by a direct penalty that measures how fragmented is this matching of the MT output with respect to the reference, where every time that the words that match basically don't constitute a consecutive n-gram run or chunk, then that consists of fragment, and we count the fragments compared to the size of them of the overall match and get a measure of fragmentation and introduce a penalty based on that. So the sort of the most important, perhaps, subcomponent in calculating this metric is this word alignment matcher, which is also heavily used in our multi-engine work that I'm going to talk about in a few minutes. So I wanted to tell you a little bit about that. So basically, this is a monolingual word alignment matcher that takes two strings, monolingual strings, and finds the best word-to-word alignment match between those two strings of words, where the restrictions are that each word in the string can match at most one word in the other string. The matches can be based not only on identity, but on stem identity or synonymy, as I pointed out before. And what this algorithm basically tries to do, it finds the alignment of highest cardinality, the most number of words that it can match, with minimal number of crossing branches, which means that basically those words are ordered to the best extent possible in the same order in two strings. So basically, in the case where we have the same word occurring multiple times in both of those strings, we prefer to align them as much as possible sort of one-to-one straight like this rather than any crossing way, because we believe that's more reflective of the correct matching between those two strings. And if we try to do an optimal search for that, the problem is actually NP-complete. That's been observed by people, other researchers in the past. So we don't do an optimal search, actually, but we do a clever search with pruning that's very fast and has, in practice, near optimal results on most practical cases. And the way we usually run this in the context of both METEOR and also the multi-engine work that I'm going to describe, is we run it as a greedy three-stage matching. We first basically do the exact matching, find the words that are exactly identical, appear in both strings, and then we take the remaining words, we run a stemmer on them and see if we can increase the size of the match by adding matches in stemming, and then we further the words that are left, we see if there are any synonymous matches based on WordNet synset information. So here's just to give you a sort of a picture of this. This is two strings that with the matcher sort of result aligned on them. So the matches there that are indicated with white links there are basically words that are identical in both strings. It doesn't matter. We don't care about capitalization, by the way. We just we ignore any differences in case. And then the words there are in yellow are basically similar, but have the same after stemming. So criticized and criticizes, country and countries can match. And then there's even a link here between leader and president that came out from WordNet.
You don't do any named entity detection before you?
No, we don't do any named entity or anything like that right now. So, so what I want you to actually see, and this is also important for the multi-engine, that we can in fact get long-range alignments here if they in fact are supported. If that is the best thing that we can do, then we'll get that. But we will suffer in the case of the METEOR. We will suffer from some penalty from these links that create crossing branches. In the case of multi-engine, this actually helps us because it allows us to capture things that basically are translations of the same thing, but in one translation or maybe appeared in the beginning of the sentence, another translation might have appeared at the end of the sentence. Okay, so the full METEOR metric basically, what it does is it explicitly runs this matcher between an MT and a reference. It does this separately for each one of the references and finds the highest cardinality matching. The matcher returns, as I said, also a fragment count that's used to calculate an average fragmentation. And the METEOR score basically is calculated as a discounted F-mean score, where the F-mean was this heavy recall, low emphasis on precision. And there's this discounting factor here that is actually exponential from this chunking score that's returned also by the matcher. So the final score, basically, what it turns out, the way this hasn't been fine-tuned very well yet on training data, but you can the greatest penalty that you can suffer here is 50% of the score. So basically, if the words are completely out of order and all the chunks are of length 1, you will get 50% of the score that you would have gotten from just the unigram-based F-mean measure. And the scores can be calculated at the sentence level, but we also do similar to what Blue does on an entire test set. We calculate aggregate scores that are calculated over the entire test set. So we accumulate all the matches, and then we calculate aggregate precision, recall, these F measures, and then an aggregate penalty that gets assigned to calculate the final score. So this is the effect of the sort of this discounting factor. That's the greater the fragmentation, the more the penalty is, and the most in the ultimate case, you get a penalty of 50%. This is sort of just an example of how the overall score would be calculated. So here here's the reference, here's the MT output. So the words that are actually matched here are indicated here. Iraqi weapons, Army in 2 weeks matched. And then we do the matching. So we calculate the unigram precision and recall, and then we calculate this F-mean. And the fragmentation here turns out to be 0.5, so we suffer a penalty here of about 6% on the score. And when we combine that, the final score comes to be 0.35. So this gives us a metric that basically is between 0 and 1. It's always normalized between 0 and 1. We can calculate it on a sentence-by-sentence basis if we want. The scores are still noisy on a sentence-by-sentence level, but not quite as noisy as Blue or modified Blue turns out. I can show you some slides about that a little bit later. And it addresses some of these weaknesses from Blue. in particular, we get significantly higher correlations with human judgments than blue does, and I can show you results on that. So this is just an example of how the reported score is on a test set. So we get the number of actual matches, how many chunks were there. That's this fragmentation. That's this measure that allows us to calculate the fragmentation. These are the total number of words in hypotheses and the references that were selected, aggregate precision, recall, F1 measure, this F-mean measure, the actual penalty that's applied on the F-mean, and the final score is the one that's reported up here. Now, so I'm going to skip some of these slides on evaluating METEOR, and I can come back to this later. But let me just tell you, METEOR is freely available. If you want to use it, we'd be happy to let you have it and run it. If you know how to run Blue, you know how to run METEOR, because we set it up exactly the same way that Blue is set up. So if you format your files for running Blue, you use those same files and you run our Perl script, and you'll get METEOR scores. Okay? You can download it from the site that's up there, and if you don't want to copy it down or you don't have a copy of my slides, just email me and I'll be happy to point you where to go. So we're happy to have people use it, and we welcome comments and bug reports and anything that you want to tell us about it. Yeah?
How often have you found that the expanding using the word net synonymy helps you? I mean, does it? So
in experiments that we've done, basically, we found that the stemming increases the size of the matches by an absolute of about 3%, and the synonymy, on average, increases it by about another 3%. So by stemming and synonymy, you increase the sizes of the matches between empty output and reference by about 6% absolute on average. And yeah.
Was there any sort of penalty for matching on a synonym or a stem and step match? Or is that
right now, we don't penalize. We recognize that those matches are probably less reliable. The greedy approach for now actually seems to be fairly reliable in the sense that we don't get a lot of errors when we look at the matchings. The kind of errors that we do get, and we want to actually do something about that, is for common function words, sometimes even though that appear multiple times in sentences, even though this restriction of minimizing the cross-branching tends to get things right, sometimes if we have a function word that might match with the same function word that appears further in the sentence where those things aren't in fact part of the same thing. So we want to penalize for that. I'm sorry?
Is that because you're using the border stemmer?
No. Even exact matches, sometimes you'll get a common function word like an article or a preposition in the beginning of the sentence that didn't occur for some reason in the reference as part of that same noun phrase or where it was, and then it occurs later in the sentence, and we will take that as a matching because we're trying to maximize cardinality. Blue does that too. Okay, I'm saying that it may be better to, in terms of an automatic metric, to actually remove those matches if they're not really part of the same phrase. And we do see some of that. Yeah?
How wedded are you to constraining cross-matching? Because if you're trying, between, say, French and English, I can see this might be useful, but Japanese and English will produce mirror images that have every which way.
Well, keep in mind that this is all monolingual, so you're saying translation that came from Japanese might be misordered, but that's okay. We want to actually capture that if they're misordered. So this is all monolingual. This is all monolingual, yes.
So I'm more of a machine learning person than a machine translation person. If I were doing something like this, my inclination would have been to say, okay, let's take 10 factors, what's the crossing factor and what are the n-gram factors on both within the best of a sentence and the cross sentences. Take it all and then just, learn, some correlation.
Right.
Is there some reason you didn't follow that approach?
Well, a student is working with me now and actually on work that grows out of this, but is going in a somewhat different direction that's doing exactly that, actually. So there's a new metric called blank that Lucian Lida at CMU is working. That was his main idea, but he's working together with me and Jaime Carbonell, and it's really doing basically what you were just saying. So.
Now for blue, one could actually set it as an objective function and then optimize statistical MT.
Right. That's right. So people, yeah, you can do the same thing, and actually you can. It's easier to do optimization type of systems to the metric with METEOR because you can actually do it with scores on a sentence by sentence level. With blue, one of the problems in optimization is you have to basically calculate score on an entire aggregate test set. So it actually complicates this process of trying to optimize the system to get the best blue score that you can with the parameters of that system. So this is actually easier, I think.
Your group has done optimization?
Our group has not done so far. I'm not actually part of the statistical MT group directly. But they haven't, to the best of my knowledge, optimized their system to METEOR. But you are welcome to do that. Any group is welcome to do that. Okay, so let me move on to the multi-engine stuff, and then I can come back, as I said, if you want to see some concrete experimental results that compare METEOR with blue and how we get better correlations with human judgments and some of the more details, I can come back to that at the end. So multi-engine. So the scientific challenge, there's sort of a scientific challenge that we're addressing and lately an engineering challenge that we're addressing as well. So the scientific challenge is basically how to combine the output of multiple MT engines into a synthetic combination output that outperforms the original in translation quality. And what we're trying to do is not just train a classifier that will tell you on a sentence-by-sentence level if you have, say, 3 systems running in parallel, for this sentence, pick output 1, for the other sentence, pick output 3, but we're actually trying to synthesize the outputs from all engines into a combined output that is, in fact, of higher, superior MT quality. So not just selecting the best system on a sentence-by-sentence basis, synthetically combining them. The engineering challenge is actually how to set up an architecture that can integrate multiple distributed translation engines and an algorithm that combines them in a common framework that supports both development and evaluation. And I'm going to say a little bit about what we're doing on that front within the Gale program that's just starting, and which is an ideal case because we're going to have their different groups participating in our consortium, each building an MT engine, and we basically want to use this multi-engine framework to have them run their MT engines distributed on their locations and combine them and build and get a combined synthetic output. So let me talk a little bit about the actual approach for synthetically combining multiple engines. So the idea is that the original engines in this approach are treated as black boxes. They're each providing just a single best translation as a string. We don't have, so far in the work that we've done in this approach, we're not using any information anymore about the source language or what words from the source language were aligned to what parts of the translation or anything like that. We just have the linear string output coming from each one of the translations engines. That simplifies our life and makes this thing applicable to a lot more scenarios that were not really applicable with other approaches in the past. So if you're trying to combine lattices, there's a lot of problem making sure that the lattice representations across systems, even if they produce them, are compatible in the sense of the indexing of the source to target mappings and so forth. So this is actually a very simple setting. These engines are black boxes. Each provide a single best translation. And what we do actually, the first thing that our engine does is that we explicitly identify and align the words that are common between any pairs of the translations using the matcher program that I showed you before. So basically, again, this is monolingual alignment. We take each one of these translations and we align explicitly what words and phrases appear in all of them, in any 2 of them, and then consequently, with transitivity, we can get the ones that occur in multiple outputs. And we do that, again, not just based on word identity, but we can do that based on these more extended criteria of stemmed words and synonymous matches as well. So then the idea is that we can use those alignments as basically as reinforcement and as indicators of the possible locations for the words into the hypotheses of combined output that we're producing. So the idea basically, if a word occurs in more translations, it's more likely to be a correct translation, and we want to increase the likelihood of putting it into our selected synthetic combination, okay? And also the alignments, or basically the positions in where those words that are common in the different translations are going to provide us with hypotheses about where to put them into the synthetic translation. So if in one translation the same word occurred in the beginning of the sentence and that word occurred in the end of the sentence in another translation, we will have two possibilities of where to put that word, but we'll still get the reinforcement factor that that word occurred in both translations. So one possibility will put it in the beginning where it occurred in translation 1. Another possibility would be to put it at the end where it occurred in translation 2. But we still have that match that tells us that word occurred in both sentences. So we basically take confidences that come from the individual engines, and right now those confidences are global. So on the global level, we basically decide how much confidence we have in each one of the engines that are providing these translations, and that confidence is basically used with any of the words that engine contributes. But again, if a word then is supported by more than one engine on a particular sentence, so if it occurred, say, in all 3 translations, then the confidence of that word is 1 in the sense of how much weight it's going to have in our synthetic combinations. Then, as I'll describe in a few minutes, we have basically a hypothesis generator then that creates a whole space of hypothesis of synthetic combinations of taking words from the different possibilities for a particular sentence. And then we create this hypothesis space, and there's a decoder that actually is then going through that hypothesis space and searches for an optimal synthetic combination of words and phrases that optimizes a scoring function that takes into account both these alignment confidence weights and a language model that's providing us score information in addition. So here's how this hypothesis space is actually constructed and how the decoding consequently works. So the algorithm builds collections of partial hypotheses of increasing length, starting from the beginning from the left going to the right of these sentences that are matched. And basically at any point, partial hypotheses are extended by selecting a next available word from one of the original systems that could be then an extension of any one of the partial hypotheses that we have at this point. So the underlying assumption that we're making here, and you'll see in a minute, this is just a crude assumption, and then we deal explicitly with the cases that of course doesn't hold, is that the sentences are essentially synchronous. So basically, every word is either aligned with another word by the matcher in another translation, or it's really to be considered as an alternative of that word. So basically, when we pick a word from one of the translations, we initially try to basically see if it's already matched with an occurrence of that word in the other translations, it'll mark that word as have already been used in the other translations. If it's not aligned, then our initial presumption is that we have to find another word. If we select a word from translation 1, we have to find another word from translation 2 to throw out, because there's probably some equivalent of that word that was not matched by the matcher or that we will want to throw out. Yeah?
What do you do when the sentences are different lengths?
So I'll talk about sort of how this assumption breaks down in a minute, what we do. Yeah?
Are you also going to talk about why you're doing things linearly and not looking at the sentence as a whole?
Well, basically, what's happening left to right here is a construction of this hypothesis space of a whole large set of synthetic combinations from which we're going to select one that we presume that we're going to score as the best scoring one. So we could construct this space in different ways. We chose to construct it as a search that's going from left to right. Okay?
So how many different engines can the algorithm support unlimited in general?
In principle, the complexity grows quite significantly with the number of engines. We've done 3 engines in our experiment so far, and it's pretty fast. The algorithm isn't a priori limited to any concrete number of engines, but the complexity of this does grow.
It's not linearly increasing.
Right. That's right. It's more than linear within the number of engines.
2 CMU system and 1 IBM in Gale.
In Gale, we'll have probably at least 3-4 systems that we'll be combining. Yeah. So, so basically, the way this goes, and we have a partial hypothesis that has some selection of words so far in the sentence. We extend it by pulling the word from one of the engines and canceling out, basically marking as used, the aligned words that are in the other hypothesis and marking those alternatives that as used. So we keep track of that with vectors that mark basically from each one of the original translations what words have been used or canceled out as being used that go with a particular synthetic combination, which is one of these multiple hypotheses that are being constructed. So these partial hypotheses are scored and ranked. We can't keep track of all possibilities, so we do a scoring and a pruning and ranking. And the decoding there actually also allows identifies situations with the language model scores where different sub-hypotheses can be combined together and pursued together. So it's cutting down on the complexity of this hypothesis space as we're going along. And then hypothesis basically can end at any point where one of the original systems proposes that the end of sentence is the next thing to next word that original system is proposing. So let me say a little bit about the scoring, and then I'll go back and tell you a little bit about how we deal with translations of different length and relax this idea of requiring an explicit cancellation of words between when we're selecting them. So the scoring is basically done using the word confidence score that I mentioned before and the language model. So the word confidence score is between 0 and 1. It's based on the engine confidence from which that word came. And we get reinforcement, as I said, from the alignment. So if you have 3 translations and the word occurs in all 3 of them, the word confidence that goes with that word when we incorporate it into any of the synthetic combinations is going to be 1. If it occurs in only one engine, the confidence of that word is the score that came from that engine. Then we get a language model score based on a standard trigram language model. And we trained a log linear combination, a weighted sum of the logs of the confidence score and the language model score to combine those 2 sources of information. And we select the best scoring hypothesis at the end using, we tried 2 things, either a total score, which introduced, as is well known, a bias toward shorter hypotheses, or we calculated an average score per word, which then actually works better and allows us to select also hypotheses that might be longer. So here are some of these additional parameters that are part of the algorithm that allows us to relax this very strict constraint that basically all of these sentences have to be presumably of equal length, and when we pick one word, we have to cancel a word on the other. So we have several parameters. One of them is this lingering word horizon, which says how long are we allowing a word to linger from a particular original translation when words following it have already been marked as used. So if we have one of the original translations, there's some word there that hasn't been used so far. If we've moved on in a sentence in our synthetic combination beyond a certain window, we'll just throw it out and say, okay, we don't think we're ever going to need to incorporate this word in our synthetic translations anymore. And that basically avoids situations where we're taking words that were not aligned across these translations and we have not been selected in a particular synthetic combination and are just hanging around there and then finding a bad place and then throwing them in late in the sentence or something like that where they wouldn't be appropriate. The other sort of window is what we call a look-ahead horizon, which tells us basically when we have words that aren't aligned and we're trying to force an alignment, pick a word from any of the alternative translations that might be an alternative for that word, don't go looking too far. So basically, how far ahead can we look ahead for an alternative for a word that has not been explicitly aligned by the matcher in order to throw that word out when we're selecting a word from another translation? And again, we have a window there that tells us don't go looking too far ahead. And the combination of these lingering word parameter and this look-ahead horizon basically takes care of the situation where the sentences are not the same length or don't actually are not consistently have alternatives of each other So those two parameters basically allow us to handle that situation. And furthermore, we actually, in this process of what we call artificial alignments, words that aren't aligned by the matcher, but we're throwing them out from one translation when we're selecting a word from another translation, we made that selection to be more strict. We require part of speech matching. So limit the search for alternatives that are not matched explicitly by the matcher to only words that have the same part of speech and fall in within this look-ahead horizon. So here's an example now of what comes out on a particular sentence when we ran this. These scores here, by the way, are METEOR scores on a sentence-by-sentence level for these particular sentences. These are three outputs from three statistical MT systems, IBM, ISI, and CMU, on one of the MT eval. I believe this was from the MT eval 2003 test at one of the sentences. And this is actually the multi-engine, the selected hypothesis that came out from our multi-engine system. It has higher METEOR scores, you can see here. This is the actual score from the actual algorithm that came out with this hypothesis. And this here, this is interesting because this points out something quite nice. So since we're creating this space of synthetic hypotheses, and we're just right now using a fairly crude scoring mechanism to pick the best one, we went and did an oracle experiment to see if we could actually, from within the space that's created on this sentence, pick the actual synthetic combination that has the best posterior score by scoring it with METEOR. What would we get? So basically, if we could pick out from this space the best translation according to any posterior scoring scoring thing like METEOR or BLUE, what would we get? And there are in fact hypotheses hiding in that space that we're not capable of selecting out yet, but that are significantly better. And we've done this oracle experiment actually on a larger scale, and I'll show you some results on that, the results in a minute. So the current system basically was developed by using Tides 2003 Arabic to English data as development data, using IBM, ISI, and CMU SMT systems, and the evaluation results were performed both on Arabic to English systems and on Chinese to English systems. The Arabic to English ones were our in-house CMU EBMT system, a system from Aptech, and a system for Sistran. And the Chinese ones were 3 Chinese translators that we actually took off the web. And let me show you some results, and these are all reported here with the METEOR scores. So so this is the results for the Arabic to English. So these are the METEOR scores of the 3 original systems. And there you can see that they perform actually fairly similarly. There's not a whole lot of difference between them. Now, this line over here shows basically if we had an oracle that just did select on a sentence-by-sentence basis the best translations from each one of the original systems, how well could we do? And it turns out that in this case, you can't do actually a whole lot of better by just selecting the best of the original 3 on a sentence-by-sentence basis. Now this is, keep in mind, also an oracle. This is the best we could do if we were just doing pick among the originals. This is the METEOR score of the actual multi-engine system that we actually get. So that's about a 6% improvement actually over the best of the originals. And this is the oracle score that I referred to before. If we could actually go into the space for each one of these and select the best hypothesis generated by our algorithm for each one of the sentences and score that system, this is sort of the ceiling or the upper bound on how well could we do with just our algorithm if we improved our sentence, our hypothesis selection algorithm for picking out the best hypothesis that we're generating. So that's another quite significant improvement, as you can see, that we can get. So that means that we're generating even better hypotheses than we're able to select out right now, but we're not, our scoring isn't sensitive enough to picking them out and getting them out. The results on the Chinese to English are somewhat similar, not quite as good as they were on the Arabic in this case. So these are the 3 original online systems. Again, they had very similar performance. Here, if you could actually, there was more differences between the actual 3 systems. So if you could actually pick which one is best on a sentence-by-sentence basis, you do quite a bit better than the original 3. Our multi-engine combination gets you basically about to the same level that you could do here with picking the best of the original 3. And once again, we see from the oracle that if we were able to pick out from the hypothesis that we're creating the best one, there's still quite a bit of room for improvement. Yeah?
Do you have results on this with BLEU score as well?
We do have results from BLEU scores that were just produced in the last few days. And the results with BLEU are quite a bit, they look quite as encouraging as they do with METEOR. And we actually looked a little bit into that. And what happens actually is that you improve significantly on the precision, you improve significantly on the recall with this approach, and you don't really change much in terms of precision, which is why BLEU doesn't show you that. Okay? That would explain, because BLEU is so precision heavy, then if you don't improve precision, you're not going to see bumps in the BLEU score. So BLEU score basically show very little improvement. The results don't get worse, but we don't see the 6% bump in improvement that we saw in the METEOR scores.
So although the algorithm isn't specific for METEOR.
No, the algorithm is not specific to METEOR at all.
But because it prefers to take words that occur everywhere, wouldn't it also improve precision?
Well, I'm telling you what the result. I can't explain why necessarily it improves significantly on recall and not on precision. But from the analysis that we've done just recently, it looks like that overall the precision doesn't go really up, but the recall does go up.
That's an empirical observation.
Yes, that's an empirical observation. Right. Okay, so let me, I can show you, if the internet connection here is still live, I can show you a live demo of this in a second. But let me make some observations about where we think this works well and where we think it doesn't work so well. So this setup is actually set in a way that if you have the more variety you have between the MT engines. If you have one engine, say, that's statistical MT that produces very different translations than a rule-based MT system, then you're more likely to get benefit from here. So the more variety you get between the engines, the more likely you are to benefit and be able to capture when it's advantageous to take pieces and words and sections from different translations. The other observation is that it actually works well in situations where the translation engines are fairly equal in quality or all of reasonably high quality. It doesn't work quite as well if you have an engine that's very good on one hand and you're trying to improve it further with an engine that's overall very bad. And the reason is that you're not sensitive enough with the crude metrics that we're using right now to pick and add things only in those few cases where the good engine is bad and the bad engine is actually a little bit better in that case. So we're more likely to pick things from the bad engine that are incorrect than we are to pick from the correct if there's a big differential between the systems.
So I'm not sure I understand how the combination works when the ordering of the translations is significantly different between. So, I mean, if the two, say, take two translations from two different engines, and if they've, completely reversed, like two phrases, for example.
Well, so what would happen is that the matcher presumably would still capture that in one it's in the beginning and one it's at the end. Okay, you would have two possible hypotheses, or you have a lot more, but you have one set of hypotheses where the position of that phrase is hypothesized by engine number one, which says that phrase is in the beginning of the sentence. Okay, in that hypothesis, you select that word, you put those words in the beginning of the sentence, and for the purpose of that hypothesis, you mark that you've canceled those words from hypothesis 3. You will never select them in hypothesis 3 later on, because the matching tells you to cancel that phrase has already been used. Okay, so that's one direction that of hypothesis will grow. Another one will be some other set of hypotheses that did not select those words from sentence 1 and has gone with selections from sentence 2 or 3, and then when you get to the end, you'll select that phrase and put it at the end from hypothesis 3, and at that point it'll cancel out those words from sentence 1, although if they're too far away, they may have been canceled out by this window horizon anyway.
Well, when you're doing a particular hypothesis,
yeah.
If you were to, and you picked a couple of words from one of the hypotheses, wouldn't you have a tendency to just pick one of the words that you've skipped from the other hypotheses and insert it in a random place because they're close to the beginning of the sentence?
So for the words that have not been aligned by the matcher.
Right.
So
the ones that are aligned.
The words that are aligned, then you have to use them only in combination with the words that they're aligned to. So
right. So say there's a word. So you pick 3 words from one.
Right.
And now the first 3 words in the other translation are aligned to things at the end of the
right.
first one. So what stops you from picking, say there's a 4-word phrase, picking 2 words and then switching to the phrase that's at the beginning of the other translation?
Nothing's stopping you from doing that, other than the fact that there will be competing hypotheses that don't do that, and some of them, it's going to be a scoring issue of which ones sort of score better.
But there's a monotonicity assumption that's going to actually cause this to be these types of sort of interleaved hypotheses to be more prominent, isn't there?
Well, with a combination of these windows that restrict the search, then it doesn't, and there's a parameter, so those are parameters that we can fine-tune. We haven't found that that's a particularly problematic thing. We don't get really mangled type of phrases moving around all over the place that are being selected as the best things because of a problem like this. But I'm not suggesting that some more well-thought constraints on how to do this might not actually help. So, okay.
So I'm not familiar enough with the different components that you use to, what technology they use. But in other places like speech recognition, they've often found that using a greater variety of techniques leads to more improvement when you do combination. I wonder whether, I'm wondering, if were any of the systems you use, say, parsing-based or radically different than, the sort of IBM style, or are they all
Well, so the Chinese experiment had basically off the web systems. I don't know much about them, but presumably those are mainly rule-based systems that were developed manually. We've done combinations of rule-based systems and statistical systems. That's where I said that the more difference, the combining 3 statistical systems is not likely to produce very strong improvements because they're trained on the same data. They're all using probably similar language models, and we're using a language model to guide this as well. It's really a setup that's not very likely to produce very significant improvements.
So do you think you're seeing improvements partially because you're starting with rule-based systems and then you're applying a language model on top of them?
That's part of it, I think. I think that if there is a rule-based system thrown in there, then the fact that we're sort of breaking up the pieces from the rule-based system, providing alternatives from other systems and applying a language model could be a significant part of what the improvement comes from, yeah.
And then, have you ever tried it with any parsing-based systems? I'm wondering, because I assume that you could it seems like the word ordering heuristics are pretty primitive, and if you threw in something with, great word ordering heuristics, that you might actually make things worse in the end, or at least not get the benefits, right? You could see how...
Yeah. There's basically what you're saying is that this could actually break up because it's not sensitive to some global structures that a system might have suggested. You could actually break down the structure that was introduced by a system that actually was very good at producing well.
Other systems have diagram model, language model, or something more sophisticated than what you're using. Have you tried anything with really that had a super sophisticated language model or that was parsing based?
We haven't tried anything like that yet. Okay.
So web-based in your the Chinese translate from the web, how do you get the confidence score for your?
Oh, I should have mentioned that. So we have 2 ways in which we actually calculated confidence scores. One is sort of the most intuitive one, is that we actually run those systems on a test set. We get, as we saw, the individual scores with METEOR for each one of them, and then we basically assign confidence based on the relative METEOR scores or BLUE scores of each one. So basically, the relative weight of each one based on their posterior METEOR scores was one way to actually score them. That's sort of the most intuitive way to do it.
But in that case, you have a little bit cheating there, right? You see the reference when you get the METEOR score.
Well, no. We can always run the system on some data that we have reference scores for, and just get a confidence for that system, and then use those confidences for data that has been unseen before. So it's not cheating in that sense. Okay.
A system confidence.
Right. That's right. We have a system confidence score, and we can do that on some held-out data for which we know we have reference translation. We can calculate the METEOR scores. The other way we've done this is actually which is quite a difference in weight. So we calculate also, instead of calculating the relative aggregate weights based on the performance of the individual systems, we've taken that test set and we've seen for how many instances of the test set did each system produce the best translation, okay? And base the weights of the confidences on that. And that can come out quite differently, because if one system is only a little bit better than another, but it's consistently better than the other, then it might beat the other one on all the sentences, and hypothetically it could get 100% weight where the other one would get 0% weight. So it produces quite a variety, a different set of weights. We haven't done enough experiments on comparing those two, but the ones we've run so far, I think, show that the second method performs slightly better than the first method. Ken, you had a question?
Yeah, I'm trying to figure out the politics here. Maybe I shouldn't.
Uh-oh. Politics?
It seems to me that evaluation metrics are in play right now, and they haven't been for a while. And they're in play for two reasons, and we can go through what they are. But the argument for what you're doing here seems to be a third and quite separate argument from those first two. And the argument here seems to be that this now produces a seat at the table for all those guys who wanted to do role-based systems and legacy systems and all that, right? And those guys would like a seat at the table, and if we don't do something, they won't have a seat.
Well, that's not really the reason why we started doing this, but I agree with you that actually is part of the outcome of this, that it actually provides room at the table for people that are producing systems that maybe standalone don't produce better results than statistical MT these days, but have significant... That's right.
Otherwise, what we're going to see is sort of like what happened in speech. Everybody's going to basically follow whatever worked best at the last bake-off.
That's right.
And that gets very boring. Right.
And I totally agree with you that I think that it's doing that, I think, is very valuable.
Politics are for why I thought evaluation metrics are in play, and this, I think, doesn't address either of them. And the two are conflicting. Okay, so one of them is Franzak gave a talk at a workshop last ACL, in which he basically said Blue's got about 2 years and that's going to run out of steam, and I don't know what to do after that. And so he's now putting down the gauntlet, saying he's open to discussion for some other metric. Wherever the metric is, he wants it to be something he can gain.
Right.
Okay. And Joe put down the gauntlet just the opposite.
Yeah.
He said, I don't believe that any of these metrics are going to produce us the best answer if they're gameable.
Right.
Because you'll just optimize whatever they're doing. Whatever they're doing is not what really matters, and all you'll do by gaming it is drive a wedge between what the metric says and what really matters. And so he's going to try to come up with a metric you can't game. Now, I can believe because this metric is gameable, he won't like it. Right?
Well, we posed it to him for Gale, and as you know, he didn't select it for Gale, but.
All right.
But actually, the folks at NIST are using this and have reported on METEOR as well as BLUE in various comparisons they've done with the Gale metric compared to the automatic metrics, and I think that's valuable.
I have a feeling that if I were Franz and wanted a gameable metric that I can use after Blue runs out of steam from his criterion, this isn't going to meet his interests either. because of course he's not going to accept the position that any that any NLP anything is going to improve anything, and this is only going to make a difference if he was wrong.
What the multi-engine is going to make a difference?
I think you're conflating the multi-engine and METEOR.
Right. Yeah. Right.
It's true that he did say that the multi-engine showed more improvements with METEOR than with Blue, but the converse is not true, right? I mean, METEOR might be useful in a number of other situations.
Right. And multi-engine might, if we make improvements, the fact that Blue doesn't show.
METEOR and Blue had to do with the set of issues that Franklin accept.
I don't know. I don't think that's true, because the differences between METEOR and Blue fundamentally are because of the importance of recall for automatic for correlations with human judgments. So we get significantly. METEOR is heavily biased to recall. Blue is a precision-based metric.
So let me now make a hypothesis here that is for a proposed evaluation metric to win out in this in-play situation, it has to appeal to two of the three constituencies that we mentioned. All right? And I think you got one.
You mentioned a few times that Blue is significantly more, or METEOR is significantly more correlated. By significantly, you mean statistically significant?
Yes.
And in practice, what are the differences in the correlation coefficients? Or
yeah, I can go back to show some things on that.
Sorry, did I miss them, or are these slides you presented? I'm boring everybody.
No. I skipped them. So this is comparison of the system-level correlations, Pearson correlation coefficients, between Blue up here, modified Blue, which is Blue, as some of you might know what modified Blue is, with arithmetic averaging over the n-grams rather than geometric averaging, so you're less biased, you're less volatile to zero scores on a sentence-by-sentence basis. And this is just unigram precision, unigram recall, balanced F1, this recall-heavy combination, and METEOR, which is this plus the penalty that we get from the ordering. Yeah.
Correlation with what? With adequacy?
Correlation with a combination of the sum of adequacy and fluency together in this case, not measured separately. Although we have done evaluations, there's some slides here that also show separate adequacy and separate fluency.
Is that multiple human judgment? Or
Yeah, this was done on this is done for the workshop last ACL on automatic metrics for summarization and MT, where we used 2003 MT eval data with human judgments coming from there. So it's I believe actually each sentence has two. There's 4 human assessors altogether, but each sentence is actually assessed by 2, and the results then are reconciled.
How many reference translations per sentence?
The references, there are 4 reference translations. This is the TIDES data, so there's 4 reference translations for each sentence. Yeah.
So one of the convincing arguments about Blue in the original paper was they didn't only show correlation between systems, they also showed correlation between the system translations and human translations, right? So they had like 5 off-the-shelf MT systems and 1 of their statistical systems, and then 2 human translations, right? And showed all those guys in the same graph. Have you done the same thing with METEOR to see? I mean, I think one of our concerns with Blue right now is not necessarily that it can't distinguish between systems, although that is a problem, but also that it can't distinguish between human translations and system translations.
Here, to answer that question, let me take you to this last slide. This is what you get when you do a histogram of Blue scores and of METEOR scores of reference translations against other reference translations, just humans against humans, okay? And what you'd like is, those are all good translations of equivalent to each other. You'd like the scores to be very close to 1 and with little variation, okay? This is what you get with METEOR. This is what you get with Blue, okay? This is I believe this is actually modified Blue, so you're not going to get just zeros. Well, maybe not, because there's this big thing here. I'm sorry?
We need to see the systems too, and you'd like to see the systems separated from the humans.
Right. We get, but this should give you an idea that we give scores that are much higher to human systems than Blue does.
Yeah, but you give scores that are much higher to systems.
Maybe everything shifted.
No, it's not. Well, so if we go back to the correlations,
What exactly are these correlations?
so this is when you have multiple systems that were that are basically for the entire test set. You had, in this case, 900 sentences. You got human judgments for all those sentences for these systems. You got blue or METEOR scores or all these scores for those systems. What is the correlation between the scores of the human judgments on one hand and the system scores on the other hand? This is the standard way that people have done this type of comparison. Yeah.
In this chart, it looks like F1 is better than F mean. So what led you to base METEOR on F mean?
Well, in the data that we originally used for training, which was 2002 data, the F mean worked significantly better than the F1. But yeah, on this set, it actually doesn't show that you get significant improvement from the F mean.
So is it only unigram precision and recall there?
This is unigram precision, unigram recall, yes.
So it means that the prior diagrams shouldn't be there in blue?
Well, this is recall is better than blue. Precision, unigram precision is worse than blue, as you can see. Yeah.
So I think I asked a same question at ACL workshop, but it's curious that Chinese correlation is lower than the Arabic correlation. And I wanted to know why that is. Does it mean that automatic metrics in general are less fit to evaluate the translations from Chinese than?
I think I didn't have an answer for you then, and I'm not sure I have one for you now.
I wonder why. How can you make sense of it?
Well, one conjecture might be that it's not shown on the slide, but in general, the scores on Chinese data are much lower than Arabic data. And my conjecture would be that humans are not as reliable at scoring bad translations.
Yeah, I think that's a good. Yeah. So let me just show you a little bit more here. So when we look at the sentence level correlations, which are much, much lower because the scores on the sentence level are extremely noisy with these metrics. But and blue, again, to be completely honest, blue was never designed to calculate scores on a sentence by sentence level. So it's not surprising that if you force it to calculate those correlations, they are extremely poor. And we're not getting, you know, orders of magnitude better, but we're doing significantly better with sentence, at the sentence level than much, much better than blue is doing on that, or even modified blue, which would not be as sensitive to the zero scores, is doing at the sentence level. And this is the scores on adequacy, fluency, and combined is what you've seen so far. So you can see here that we're doing actually significantly more. We're better at the sentence level of correlating with human judgments of adequacy than the improvements are much more pronounced on adequacy than they are on fluency. Okay, so which is I don't know if that's surprising or not surprising, but basically adequacy has to do with getting. I guess it's not surprising to a large extent because adequacy has to do with whether in fact you got the correct meaning from the original sentence, right? So recall is much more important for adequacy. Because if you miss parts of translation, adequacy should really suffer because you didn't actually get that from the original source, and that would be captured by recall, right? So because we're actually emphasizing more on recall, we're getting better correlations with adequacy. We are getting also better correlations with fluency, but not quite as pronounced.
So the fact that sentence level correlation is much lower than system level correlation.
Right.
It means that every system that you have has a huge variation.
Right. So this is what the scatter plots look like on the sentence correlation. So again, these are the human scores assigned to those sentences. These are the automatic scores assigned by the metric. This is METEOR. This is blue. And you can see that it's still extremely noisy, right? I mean, basically, you get a huge variation here for any individual human score. You get sentences that have automatic scores all over the place. But this is significantly a better looking plot, I think, than this. So again, this is actually raw BLEU, so you can see here all these dots at the bottom that are basically sentences for which BLEU gave a 0 score because of the geometric averaging of the n-grams. And then finally, I showed you this histogram here that sort of says that at least we believe that on a sentence-by-sentence basis, METEOR, this is again running on scoring reference translations against the other reference translations. So you'd like to have scores that are as close to 1 to these because these are presumably really paraphrases of each other. And we don't get scores quite up to 1, but we get average about 0.65 with METEOR, which is quite good, I think. Okay, we're already quarter to noon. I could show some multi-engine, 1 or 2 examples from the multi-engine if people want to see that. If not, I can show that in private to people this afternoon. So.
This is the demo you have?
Yeah. Do people want to stay and take a look?
People would enjoy.
Okay. Well, let me see if I can get that up quickly. I had to reboot here. So.
Just also say we'll be having lunch with Alon just in the cafeteria, our regular table in the back, so anyone's welcome to join us too.
Okay, let's see if this works.
The fixed point is 9,000.
Yeah, I know, but we set it up on a different port today. Okay. Let's see. Oh, it's working. Okay. So, wow, that was fast. So here you see the 3 original translations, and what I can show you here, this is the final output, the multi-engine translation in this hypothesis space selected for this combination of these 3. And we can see by clicking here on the words actually where each one of these words came out from. This is not necessarily perfect translation, but so the dark blue shows basically where it selected the word from which hypothesis. The light blue show that this word was actually occurred in these other hypotheses too, so it was aligned by the matcher. So when we selected it from here, it canceled out these words from here, and they were no longer available in the next step to be selected. Okay? And is only occurred here, the top. So this is also interesting. So in this version that we have running here, because we have ranked 5th in here, ranked 5th in, and presumably there, well, I don't see it actually here. So basically this actually shows that we chose an entire phrase from here. So ranked 5th in was selected as an entire phrase rather than selecting things word by word. And we have a condition now in there that sort of tells you when to actually continue with a phrase from one hypothesis rather than opening it up for words from the other hypothesis after the first word of that phrase. The source language here was, I believe, Arabic. So let's see. So well, you can see. So here, ranked were by the matcher, and ranked in place. This must have come from a WordNet synonymy. It's actually not quite necessarily the right match here, but. So 5th occurs in all 3 in.
Where did 2 and 2 the 8th come from?
Over here? Yeah. Yeah, that's the wrong 2, but export. So this is nice. You see export here and exporting here. That's was captured by the this 2 is unfortunate that it got stuck in here. The 8th in the production. Pick. So one thing that I can also show you is sort of the step-by-step expansion of the hypothesis if I do it step-by-step in a minute. So this is a nice example because here translation number 2, which I will tell you in secret actually came from ISI and it was a good system overall, overall produces the most accurate translations on this test set. But here in this sentence, the ISI translation actually missed the verb of the sentence. It's from Arabic. So you see the Afghan authorities on Saturday, the formation of the 4 committees, and here there's announced, and here there's announced. Here there's announced, and yeah, here there's announced too. And what we managed to do here is in the combined hypothesis, we actually just took that verb and put it exactly in the right place. So the Afghan authorities on Saturday announced. So that basically, and then it continues fairly consistently picking out most of the translation from translation number 2. So this is a really nice example of where we could compensate for an error in translation number 2. The Afghan authorities on Saturday announced the formation of 4 committees of government to speed up the process of disarmament and mobilization of fighters, leaders of the war who still have significant influence. So this one is actually, so of course, we picked some nice examples for this. It doesn't always do equally as good as you can see. Let me see if there's some other just interesting matches here that come out. 4 committees, government. So right now, actually, what we've done is if that entire phrase occurs in multiple original systems, then when we start it, we'll just continue with that phrase rather than considering, and that also helps with some sticking in words that are lingering around from other hypotheses. Let's see. This is nice. Look at this. Speed and accelerate. That came from WordNet. So the matcher got that those things are equivalents of each other. Okay, I can show you some other sentences, but that's basically the idea. Okay?
Thank you very much. 2 minutes per question, or we should just continue at lunch.
Does anyone want to look some more at this before I bring it down?
Do a step-by-step example. Well, if you go back